Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The conferral of the 19th of 95 Nobel Prize in Chemistry to Paul J., Crutzen, Mario J., Molina, and F. Sherwood Rowland represented a watershed moment in the history of environmental science. It was a formal acknowledgement that human industrial activity could precipitate changes on a planetary scale, altering the fundamental chemical composition of the Earth's atmosphere. The laureates' collective work, culminating in the identification of chlorofluorocarbons as potent agents of stratospheric ozone depletion, constructed a new paradigm for understanding the intricate connectivity of global systems. This essay undertakes a profound and meticulous evaluation of the core claims, intellectual architecture, and evidentiary reasoning presented within the 3 Nobel lectures delivered by the laureates. Through a section-by-section analysis of each address, this inquiry will illuminate the precise scientific arguments that built the case against chlorofluorocarbons, examining the internal logic, the methodological innovations, and the conceptual frameworks that underpinned one of the most consequential scientific discoveries of the 20th century. The focus remains exclusively on the work as presented by its authors in their culminating 1995 addresses, assessing the scientific narrative they constructed to explain their path from foundational atmospheric chemistry to a global environmental crisis and its eventual, though incomplete, resolution. Section 1 Paul J. Crutzen's Foundational Framework of Atmospheric Catalytic Cycles. Paul J. Crutzen's Nobel Lecture, titled My Life with O3, NOx and Other Isox Compounds, provides the essential prologue to the chlorofluorocarbon story. His address functions as an intellectual autobiography that establishes the foundational understanding of ozone chemistry upon which all subsequent discoveries were built. A central claim within Crutzen's presentation is that the stratospheric ozone layer, far from being a static shield, exists in a dynamic equilibrium governed by catalytic chemical cycles. He details his work from the late 1960s and early 1970s, which first identified the crucial role of nitrogen oxides, collectively termed NOx, as natural regulators of stratospheric ozone. Crutzen explains the Chapman mechanism, the initial model of ozone chemistry, which involved a simple 4-step process of oxygen photolysis and ozone formation and destruction. Its critical contribution, as he recounts it, was the realization that this simple model predicted ozone concentrations far higher than those observed. This discrepancy, it argues, pointed toward the existence of more efficient, catalytic ozone destruction. Crutzen's lecture meticulously evaluates his own hypothesis that nitrogen oxides, originating from the microbial decomposition of nitrous oxide released from the soil and oceans, could provide such a pathway. He presents the core catalytic cycle with academic clarity. The cycle begins when a nitric oxide molecule reacts with an ozone molecule, yielding a nitrogen dioxide molecule and a diatomic oxygen molecule. Subsequently, the nitrogen dioxide molecule reacts with a free oxygen atom, which is available in the stratosphere from the photolysis of ozone and oxygen, to regenerate the original nitric oxide molecule and produce another diatomic oxygen molecule. The net result is the conversion of an ozone molecule and an oxygen atom into 2 diatomic oxygen molecules, with a nitric oxide molecule emerging unscathed, ready to initiate another cycle. The evaluation of this claim within his lecture rests on its explanatory power. It resolved the significant discrepancy between the Chapman theory and atmospheric measurements, providing a chemically plausible mechanism for the natural regulation of the ozone layer. Crutzen's argument is a powerful demonstration of how theoretical chemistry, when confronted with empirical data, can lead to a more complex and accurate model of a natural system. He effectively frames the stratosphere as a sensitive chemical reactor, a system whose stability depends on the delicate balance of trace compounds. This conceptualization of a system vulnerable to catalytic poisoning is the intellectual bedrock upon which the later work of Rowland and Molina would be constructed. His lecture, with a certain professorial charm, establishes the precedent that a very small quantity of a chemical catalyst could have a disproportionately large effect on the global ozone budget, a concept that was anything but obvious at the time. Section 2F showed Rowland's articulation of the chlorofluorocarbon threat, TEF. Sherwood-Rowland's lecture, Chlorofluorocarbons and Ozone Depletion, presents the central thesis of the discovery. It is a masterclass in scientific storytelling, methodically constructing a chain of reasoning from an innocuous industrial product to a global atmospheric menace. The first core claim Rowland evaluates is the extraordinary chemical stability and long atmospheric lifetime of chlorofluorocarbons, or CFC. He presents evidence from atmospheric measurements initiated in the early 1970s, showing that the concentrations of specific compounds like trichlorofluoromethane, known as CFC11, and dichlorodifluoromethane, known as CFC12, were rising in direct proportion to their cumulative industrial production. This, he argues, confirmed their inertness in the troposphere. They were subject to no significant known removal processes such as Raynaud, oxidation, or photolysis in the lower atmosphere. The evaluation of this point is grounded in robust empirical data. The correlation between production figures and measured concentrations formed an undeniable testament to the compounds, persistence and accumulation. The second major claim in Rowland's lecture details the inevitable fate of these persistent molecules. He posits that the only atmospheric sink for these CFCs is photodissociation, high energy, ultraviolet radiation in the mid-stratosphere, at altitudes above 25 kilometers. Rowland explains the underlying physics. With precision, the carbon-chlorine chemical bond is susceptible to cleavage by ultraviolet light of wavelengths shorter than approximately 220 nanometers, a portion of the solar spectrum that is filtered out by the ozone layer itself and thus fails to penetrate to the troposphere. His argument follows a simple, yet powerful, line of logic. If the molecules are accumulating in the atmosphere and their only removal mechanism is in the stratosphere, their eventual transport to these high altitudes is a certainty. He presents the specific chemical reaction for a compound like trichlorofluoromethane, which upon absorbing a high-energy photon, breaks apart to yield the dichlorofluoromethane radical and a free chlorine atom. This claim was, at its inception, a theoretical prediction based on established principles of photochemistry. Its strength lay in its logical inevitability, given the premises of CFC stability and atmospheric circulation. The third and most consequential claim, articulated by Rowland, is the catalytic cycle of ozone destruction initiated by the released chlorine atom. This is the intellectual crescendo of his lecture. He presents the two-step mechanism that mirrors the nitrogen oxide cycle previously established by Crutzen, yet with far greater efficiency. First, a single chlorine atom reacts with an ozone molecule, producing a chlorine monoxide radical and a standard diatomic oxygen molecule. Second, the chlorine monoxide radical reacts with a free oxygen atom, which is prevalent at these altitudes, to regenerate the free chlorine atom and create another diatomic oxygen molecule. Rowland emphasizes the catalytic nature of this process. The chlorine atom acts as a chemical catalyst, initiating the destruction of an ozone molecule and emerging from the sequence ready to begin again. He provides the stunning calculation that a single chlorine atom could, on average, destroy approximately 100,000 ozone molecules before it is eventually removed from the stratosphere by forming a more stable reservoir species, such as hydrogen chloride. The evaluation of this claim lies in its profound implications. It transformed CFCs from benign, ascending tracers into potent, ozone-destroying agents. Rowland's lecture presents this chain of reasoning as an unbroken sequence, each step logically following from the last, constructing an argument of immense predictive power that demanded urgent consideration, a quiet but firm intellectual alarm bell. His tone throughout conveys the weight of this realization, a discovery born from academic curiosity that suddenly acquired immense societal importance. Section 3 Mario J. Molina's elucidation of polar heterogeneous chemistry. Marisa J. Molina's lecture, Polar Ozone Depletion, addresses the dramatic and unforeseen development that confirmed the ozone depletion hypothesis in the most startling way imaginable, the discovery of the Antarctic ozone hole. His presentation focuses on the critical scientific puzzle that the ozone hole presented. The first claim Molina evaluates is the profound inadequacy of the existing gas phase chemical models, including the one he and Rowland had pioneered, to explain the observed reality over Antarctica. He explains that the seasonal loss of ozone in the polar vortex was both far more rapid and far more complete than any of their models had predicted. The existing theory, based solely on reactions occurring in the gaseous state, could account for ozone depletion measured in a few percent over many decades. It could in no way explain the observed springtime depletion approaching 50% or more in a matter of weeks. The evaluation of this claim is a testament to scientific integrity. Molina directly confronts the limitations of his own foundational work, using the discrepancy as a signpost pointing toward a new, undiscovered chemical mechanism. This leads to the central, and most innovative, claim of Molina's lecture, the critical role of heterogeneous chemistry occurring on the surfaces of polar stratospheric clouds, or PSE. These clouds, composed of ice and nitric acid hydrates, form only in the extreme cold of the polar winter stratosphere, with temperatures dropping below 195 Kelvin. Molina's key insight, developed with his research group, was that these ice crystal surfaces could act as microscopic catalytic sites, facilitating chemical reactions that are exceedingly slow in the gas phase. He presents a specific and crucial reaction, the interaction between two relatively stable chlorine reservoir species, chlorine nitrate and hydrogen chloride. In the gas phase, these two molecules react with each other at a negligible rate. However, Molina claims that on the surface of a polar stratospheric cloud particle, the reaction proceeds with remarkable efficiency. Gaseous chlorine nitrate collides with a hydrogen chloride molecule that is adsorbed onto the ice surface, producing molecular chlorine gas, which is released back into the atmosphere as nitric acid, which remains sequestered within the ice par. The evaluation of this proposed mechanism reveals its explanatory elegance. It solved two mysteries at once. First, it provided a pathway for the rapid conversion of inert reservoir forms of chlorine into a photochemically active form, molecular chlorine. When the sun returns to the Antarctic in the spring, this accumulated molecular chlorine is rapidly photolysed by visible light, releasing a massive burst of free chlorine atoms that initiate catastrophic ozone destruction. Second, by sequestering nitric acid in the ice particles, which then slowly sediment out of the stratosphere, the mechanism explained the observed denoxification of the polar vortex. This removal of nitrogen oxides is critically important because these nitrogen compounds would otherwise react with chlorine monoxide to form chlorine nitrate, thereby terminating the ozone-destroying catalytic cycle. By removing the nitrogen oxides, the heterogeneous reactions on PSEs effectively remove the brakes from the chlorine catalytic cycle, allowing it to proceed with devastating efficiency. Molina's lecture thus presents a picture of a complex, synergistic process, a perfect chemical storm created by the unique combination of industrial pollutants, extreme cold, and polar atmospheric dynamics. His work provided the definitive chemical explanation for the ozone hole, transforming it from a mysterious anomaly into a predictable, albeit terrifying, consequence of chlorofluorocarbon emissions. The subtle weight of the situation is that the very compounds that would normally moderate chlorines are taken out of play by the unique polar environment, an irony that Molina's detailed explanation makes chillingly. Conclusion: the 1995 Nobel Lectures of Crutzen, Rowland, and Molina, when evaluated as a cohesive scientific narrative, present an unassailable case for the anthropogenic depletion of the stratospheric ozone layer. This essay's analysis of their individual claims reveals a powerful intellectual progression. Crutzen's work established the fundamental paradigm of a stratospheric system governed by delicate catalytic balances a system inherently vulnerable to perturbation by trace chemical species. His evaluation of the nitrogen oxide cycle provided the conceptual blueprint for understanding catalytic destruction. Rowland's lecture then masterfully identified the specific agent of perturbation, the chlorofluorocarbons, and articulated the direct causal chain linking their industrial production to the release of chlorine atoms in the stratosphere. His evaluation of the CFC life cycle, from tropospheric accumulation to stratospheric photolysis and subsequent catalytic ozone destruction, formed the central, predictive hypothesis. Finally, Molina's lecture provided the crucial denouement, explaining the shocking reality of the Antarctic ozone hole through the novel mechanism of heterogeneous chemistry on polar stratospheric clouds. His claims regarding chlorine activation and denoxification resolved the apparent inconsistencies between the original theory and the dramatic polar observations, solidifying the scientific understanding of the entire process. Together, these three addresses encapsulate a triumph of the scientific method, a journey from fundamental curiosity about atmospheric composition to a predictive theory with profound global implications, and ultimately to the empirical confirmation and refinement of that theory in the face of new and startling evidence. The internal claims of each lecture, from the efficiency of the NOx cycle to the persistence of CFCs and the surface chemistry of PSEs, are supported by a rigorous combination of theoretical calculation, laboratory experiment, and direct atmospheric measurement. The laureates' work, as presented in their own words, stands as a testament to the power of interdisciplinary science to unravel complex environmental problems and, in doing so, to provide a rational basis for global policy action. Their collective legacy, meticulously detailed in these lectures, is the definitive demonstration that a seemingly localized human action can indeed have far-reaching and unintended consequences for the shared planetary environment, a lesson of enduring significance.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.